Somewhere in a bed of eelgrass, maybe 15 feet down, there's a scallop lying on the sand with its shell open about 1/4 of an inch. Along the soft rim of tissue inside that gap, there's a row of small, round points. They catch light the way a cat's eyes catch headlights on a back road. Blue, sometimes green, faintly metallic, spaced out along the edge like rivets. Their eyes, every one of them. A single scallop can carry 200 of them, and each one is looking at something. Now, most of us learned somewhere along the way that a scallop is a fairly simple animal. It has no brain in the sense you'd recognize. Its nervous system is built out of a few ganglia, clumps of nerve cells wired together, and that's the whole command structure. 200 eyes reporting to no head at all. But the eyes themselves are the strange part, and it took a very long time and some extremely cold electron microscopy before anyone could describe what's actually inside one. Behind the pupil of a scallop eye, at the very back, there's a curved reflector, a mirror. Your eye bends light through a lens. The scallop bounces it off a concave surface at the back of the eye, which is the same basic architecture as the large telescopes we build on mountaintops to look at galaxies. And in 2017, a team working at the Weizmann Institute in Israel, led by Benjamin Palmer and Leah Adadi, froze scallop eyes fast enough to lock the water in them in place, and then imaged them. What they found and published in the journal Science is worth taking slowly, because the details are where the whole thing turns. The mirror is made of guanine, same molecule that sits in your DNA, grown as flat crystals. Those crystals are square, not roughly square, not squarish. Square with flat edges, laid down side by side like tile on a bathroom floor, edge to edge, so the surface comes out smooth instead of pebbled. Guanine doesn't normally grow that way. Left to its own devices, it forms a different shape entirely. Something in that animal is forcing the crystal habit into a shape that tiles cleanly, because a mosaic of squares leaves fewer gaps and scatters less light than a mosaic of any other shape it could have used. Then those tiles are stacked, 20 to 30 layers deep, each layer aligned with the one under it, with a thin cushion of cytoplasm between them. The thickness of the crystal and the thickness of the gap decide which wavelengths bounce back and which ones pass through. And the thicknesses in a scallop's mirror are tuned to the color of light that survives in the water a scallop lives in. Coastal water, green and blue-green, everything red already stripped out by the first few yards. And at the front of that mirror, in the light path, there isn't one retina. There are two of them, stacked, sitting at slightly different distances from the mirror, which is exactly what you'd do if you had one optic and wanted two focal planes out of it. The far retina gets a sharp image of what's straight ahead. The near retina gets what's off to the sides. The scallop is running a wide field and a narrow field through the same aperture. The team also found that the mirror isn't a perfect sphere. It's flattened and tilted in a way that pushes the sharpest part of the image onto the retina instead of off to the side of it, which is the correction you make when your mirror sits off-axis and you don't want the picture smeared. So let me lay out what we're actually looking at. A curved reflector, segmented into tiles, whose shape is controlled to reduce scatter, layered to a thickness that selects a specific band of wavelengths, shaped off-sphere to correct aberration, feeding two detectors at two focal planes. If an engineer handed you that on paper, without telling you where it came from, you would not describe it as something that resembles a telescope. You'd describe it as a telescope, and then you'd ask about the manufacturing tolerances. And that word is the thing I want to pull on, because there's a habit built into how we talk about animals. And once you notice it, you can't stop noticing it. We say the scallop's eye is like a telescope. We say the mantis shrimp's club is like a hammer. We say the shark has a kind of natural GPS, that the octopus arm works something like a robot, that a sponge's skeleton is nature's version of fiber optics. Technology is the thing we do. Animals resemble it. They arrive at a shape that reminds us of our own work, and we hand them a compliment shaped like a comparison. That's backwards. And I think it's worth a couple of hours to see exactly how backwards it is, because there's a working definition of a device that most engineers would sign off on. A device is a physical object built to a specification. It exploits a known working principle. It performs within a stated range of conditions, which is another way of saying it has tolerances. And it fails in characteristic ways when you push it past them, which is another way of saying it has failure modes. Specification, working principle, tolerances, failure modes. That's the whole test. Nothing in it says anything about who built the thing, or whether the builder understood what they were doing, or whether it came out of a factory floor or out of a fold of tissue on the edge of a mollusk. And the animals in the ocean pass that test. Not loosely, not by charitable interpretation. They pass it the way a component passes an inspection, with numbers you can write down. So that's the walk. Discipline by discipline. The way you'd move through an engineering school, looking at what the ocean has in each department: optics, mechanics, fluids, materials, sensors. And for each one, stating the specification out loud instead of standing back and admiring it. Some of these you'll have heard of. A few of them I'd bet money you haven't. And there's something at the end of it, a difference between their machines and ours, that only shows up once you've gone through enough specifications to see the pattern. It isn't the difference most people assume. Start with light, because light in the ocean is the hardest engineering problem there is. And the ocean has more solutions to it than any other place on the planet. Here's what light does when it goes into seawater. It dies in a very particular order. Red goes first. In clear, open ocean, most of the red is gone by about 30 feet down. Orange follows, then yellow, then green. Blue holds on the longest, somewhere in the range of 450 to 480 nanometers, and even blue is essentially finished by around 3,000 feet. Below that, there's no sunlight in any useful sense. There's a zone people call the twilight zone, roughly 650 feet down to 3,000 feet, where something still filters through, but it's a blue so dim your eye would need half an hour of adjustment to register it at all. Beneath that, the midnight zone, where the only light is light that something alive decided to make. That's the operating environment. Dim, monochromatic, and getting more monochromatic with every foot. An engineer looking at that spec sheet would say a few things right away. First, throw away color correction across the whole visible spectrum, because there is no whole visible spectrum down there. Optimize hard for one narrow band. Second, every photon matters, so your losses have to be tiny, and scattering is the enemy. Third, if there's almost no light, either build a bigger aperture or find a way to gather light across a wider area and funnel it inward. Fourth, whatever you build has to work while it's soaking wet, at pressure, at low temperature, and it has to keep working for years with no cleaning cycle and no replacement parts shipped in. Now go look at what's actually down there. Every one of those design responses is present, executed several different ways, by animals that are not remotely related to each other. The scallop's mirror is the first one, and it's worth understanding why a mirror at all, because that choice isn't obvious. A lens works by refraction. Light slows when it enters a denser medium, and it bends. The trouble is that different colors bend by different amounts, which gives you chromatic aberration, the colored fringing you see around bright objects in cheap binoculars. Fixing that inside a lens system means adding more glass with different properties, which costs you light and adds weight. A mirror doesn't have that problem. Reflection doesn't care about wavelength the same way. Every color comes off at the same angle. That's precisely why Sirius Astronomy abandoned lens telescopes more than a century ago and went to mirrors. And it's why, At the bottom of the light budget, a mirror is the right call. There's a second reason too, and it has to do with room. A mirror folds the light path back on itself. The light comes in, travels to the back of the eye, and travels forward again to hit the retina. That means you can get a long focal length inside a short eye. For an animal that has to fit 200 of these along the edge of a shell, each one roughly a millimeter across, about the size of a poppy seed, folding the path is the only way the geometry closes at all. So that's the specification, stated plainly. Focal length achieved in a package under 1/10 of an inch, reflector optimized for the 400 to 500 nanometer band. Aberration corrected by shaping the reflector away from a true sphere. 2 detector planes serviced by 1 optic, and the whole assembly submerged permanently in salt water at ambient temperature. Now the tolerances, because this is where these things get uncomfortable, the color a stack of thin layers reflects depends on how thick the layers are. That's the same physics that makes a soap bubble shimmer and an oil slick go rainbow. Change the thickness, and you change the color. The layers in a scallop's mirror are on the order of 80 nanometers of crystal separated by a similar cushion of cytoplasm. To hold the reflection band where it needs to sit, those thicknesses have to be controlled within a few tens of nanometers, repeated across 20 to 30 layers, across the entire curved surface, across 200 separate eyes on one animal. Miss the thickness and the mirror still reflects. It just reflects the wrong color, in the wrong place, and the scallop's eye gets dimmer and blurrier without ever visibly breaking. That's the failure mode. Quiet degradation, not catastrophe. The same failure mode a badly coated camera lens has. And here's the part that stayed with me. The crystals are grown inside little membrane-bound compartments in the cells. The compartment shapes the crystal. Change the compartment, change the tile, which means the square edges, the flat faces, the whole reason the mosaic tiles cleanly, are the product of a mold that the animal builds out of membrane, one crystal at a time, while the eye is in service. Nobody shuts the eye down to install the mirror. The mirror goes in while the scallop is watching. We do have segmented mirrors. The big ones on Mauna Kea are made of 36 hexagonal glass segments, each one ground and polished separately, then held in alignment by a system of actuators that adjust them thousands of times a second to fight sag and wind and temperature. It took a long argument in the astronomy community to accept that a segmented mirror could even work, because every seam is a place where the image can degrade. The scallop's answer to the seam problem is to use a shape that leaves no seam wide enough to matter, and to make the segment small enough that the surface reads as continuous to the wavelength being handled. That's a legitimate engineering choice with a legitimate trade-off, and it was made in tissue. What does the scallop do with all this? Less than you'd hope, and more than you'd think. Scallops don't build a rich picture of the world the way you do. With no central brain to fuse 200 viewpoints, they can't be constructing a panoramic image. What the eyes seem to be for is motion and shape at a coarse level. A dark object moving against the background light. Particles drifting past at a density worth opening up for, since scallops feed by filtering. And a shadow arriving too fast, which triggers the response scallops are famous for, where the animal claps its shell and rockets off the bottom in a series of ungainly hops. I've watched footage of that escape a dozen times, and it never stops being funny. This armored dinner plate flapping away through the eelgrass, like a set of chattering teeth. It's also the output of the optical system. The eyes are the trigger. Everything else is the actuator. One more detail, and it's the one that sets up everything that follows. Those eyes sit on the mantle edge, right at the shell opening, which is the single most exposed piece of real estate on the animal. Crabs bite it, fish nip it, scallops lose eyes, and they regrow them. New eye, new mirror, new stack of tiles, laid down again from scratch on a living rim of tissue, while the rest of the array keeps working. Try to picture the equivalent in any object you own. Now let's take the same problem and hand it to an animal with no eyes at all. In the Caribbean, under coral rubble and in reef crevices, there's a brittle star called Ophiocoma wentii. Brittle stars are echinoderms, cousins of sea stars and urchins. This one has 5 long, whip-like arms coming off a central disc, and during the day it's a deep, almost chocolate brown. At night it goes pale and banded. It changes color on a daily cycle. It also runs from shadows. Put a dark object over it, and it hauls itself into a crevice. Which is strange because a brittle star has no eyes. It has no head. It has a nerve ring and radial nerves and a skeleton made of calcite, the same mineral as limestone and marble. In 2001, Joanna Eisenberg and colleagues published work in Nature explaining where the light detection is happening, and the answer was in the skeleton itself. The brittle star's skeletal plates, on the upper surface of the arms, are studded with an array of tiny bumps. Under the microscope, those bumps turn out to be lenses, rounded, regular, arranged in a repeating grid, each one about 40 microns across, roughly half the width of a human hair. And underneath each lens in the tissue sit bundles of nerve fibers. The animal's armor is also its optics. The same calcite that keeps a crab from crushing it is shaped, at the surface, into a micro-lens array. Now, calcite is a difficult material to make lenses out of, and the reason is a property called birefringence. Calcite splits light into 2 rays that travel at different speeds and bend by different amounts. This is not a subtle effect. Put a clear rhumb of Iceland spar on a printed page and you see the text twice, offset. Vikings may have used that property to find the sun through cloud. It's a lovely thing to look at, and it's an absolute disaster in a lens, because every point in the world would map to 2 points on your detector. There's exactly one way out. Calcite has a crystal axis, and light traveling straight down that axis doesn't split. Align the optical axis of the lens with the crystallographic axis of the calcite, and the double image collapses back into one. Every single lens in that array is aligned that way. Thousands of them, across the arms of the animal, all grown with the crystal axis pointing along the direction the light will travel. That alignment is not something you get by accident from a mineral precipitating in tissue. It's a specification, and the specification is being met at every site. There's more. A simple spherical lens suffers from spherical aberration, where rays coming through the edge focus closer than rays coming through the middle, and the result is a soft, haloed image. The brittle star lenses aren't simple spheres. Their profile is compensated, flattened in the way that pulls the edge rays and the center rays back toward the same focus. When the team ran the actual test, laying light-sensitive photoresist under the array and illuminating it, they got sharp exposed spots under the lens centers, the lens's focus, measurably to a point, at a distance that lands right where the nerve bundles are. So the specification for that device reads, micro-lens array, aperture roughly 40 microns, birefringence eliminated by crystallographic alignment, spherical aberration reduced by profile control, focal plane matched to the depth of the receptor tissue, integrated into a load-bearing structure. Load-bearing is the part that ought to stop you. This is a lens array that is also the animal's skeleton. In our world, those are separate departments with separate materials and separate suppliers. Here it's one piece of mineral doing both, and it has to satisfy both sets of requirements at once without compromising either past the point of usefulness. And the brittle star wasn't the first animal to make calcite behave. It was late to it by about 400 million years. Trilobites had eyes made of calcite, actual mineral lenses, sitting in the head shield, and because they were mineral, they fossilized, which means we can hold a 400 million-year-old eye up to the light and look through it. Nothing else in the fossil record gives you that. Most trilobite eyes were compound, with a lot of small lenses under a single membrane. One group, the phacopids, did something else. Their eyes had large separate lenses, sometimes only a few hundred of them, each with its own gap, each one a substantial piece of clear calcite, with the crystal axis pointed the right way to kill the double image, which is the same trick the brittle star uses. In 1975, Ewan Clarkson and Riccardo Levi-Setti published a paper in Nature about what they found inside those lenses. Under the upper lens unit, there's a second unit, made of material with a different refractive index, and the boundary between them isn't flat. It's a curve, wavy in profile. And when they traced rays through it and built a large-scale physical model to check, the curve turned out to correct spherical aberration. Edge rays and center rays land together. Then they noticed what the curve was. In the 1600s, René Descartes worked out the surface shapes that would focus light without aberration. Christian Huygens did related work. These are foundational results in optics, derived on paper, by two of the sharpest people who ever sat down with the problem. The interface inside the trilobite lens has the form of those surfaces. Clarkson and Levi-Setti titled the paper after them. I want to be accurate about the state of this because it's a claim that gets repeated carelessly. The doublet interpretation has been widely accepted for decades, and it's still the standard reading. Later work, including analysis of magnesium-rich structures inside the lenses, has argued about what the second material actually was and how the two units formed. And there's an ongoing conversation about whether some of these eyes worked as bifocals rather than as a single corrected optic. The correction itself, the wavy interface doing optical work, has held up. The details of the recipe are still being argued. What isn't in doubt is that the animal is gone. The phacopids died out in the late Devonian, in one of the mass extinctions, something like 360 million years ago. The device outlived its manufacturer by a margin that makes every human artifact look like a rounding error, and it's still sitting in the rock, still transmitting, still bending light onto a focus that no longer has a retina under it. Now, mirrors and mineral lenses are one family of answers. There's a second family, and it's the one most animals with eyes actually use, including you. Your eye has a lens in it. It's soft, it's flexible, and muscles pull on it to change its shape and change your focus. It also has a cornea out front. And in air, the cornea does most of your focusing work because the jump in refractive index from air to tissue is large. Underwater, that whole scheme collapses. The cornea is mostly water. Water on water is barely any index change at all, so the cornea stops focusing almost entirely, which is why your vision goes blurry the second you open your eyes in a pool, and why a diving mask fixes it by putting a pocket of air back in front of your cornea. A fish gets no mask. The fish has to do all the focusing with the lens alone, and that forces a hard constraint. To get enough bending power out of a lens surrounded by water, the lens has to be nearly spherical, and it has to be dense. A sphere is a bad lens. That's the problem. A uniform glass sphere has terrible spherical aberration. Light through the rim focuses well short of light through the middle, and the image is a smear. Any optician will tell you that a ball of glass is the worst starting point you could pick. Fish lenses are spheres. Squid lenses are spheres. And they're sharp. The way out was described theoretically by James Clerk Maxwell in 1854, long before anyone knew what was inside a fisheye. Maxwell showed that if you could make a sphere whose refractive index changed smoothly from the center outward, following the right curve, you could get a sphere that focused without aberration. It's a beautiful result, and for a century it was mostly a curiosity, because nobody could manufacture glass with a controlled internal gradient. Cut open a fish lens and measure the index across it, and that's what's there. High in the middle, around 1.52, falling off smoothly toward the surface. down near 1.35, which is close to the water outside. A continuous gradient, no interfaces, no seams. Light entering the rim travels through less optically dense material than light entering the center, and the two arrive at the same place. There's a companion number. Measure the distance from the center of the lens to the retina and divide by the radius of the lens across fish, across squid, across seals. You keep getting roughly 2.5. It's called Matheson's ratio, after the 19th century physicist who noticed it, and it holds across animals with nothing in common except that they all have to see through water. That's a design constant. It's what happens when the same physics constrains the same problem in wildly different bodies. The manufacturing is the part I find hardest to shrug at. There's no glass, no doping, no furnace. The gradient is made out of protein concentration. Crystalline proteins packed densely in the core and progressively less densely toward the surface, with the packing arranged so the material stays clear instead of scattering. In squid, work by Alison Sweeney's group at Yale showed how the proteins do it. The molecules carry variable numbers of linking patches, and the number of patches sets how tightly they pack, so the animal can dial the local density by changing which version of the protein it deposits at that radius. A gradient built by chemistry rather than by grinding. And the whole lens is alive. It has no blood supply in the center. The cells there lose their nuclei and their internal machinery to stay transparent, which means they can never be replaced, which means the lens you grow early has to last. That's the tolerance, and the failure mode is cataract, the same one that comes for us. The deep sea takes the lens and does stranger things with it. 2,500 feet down in the Pacific, there's a fish called Macropinna microstoma, the barrelly. And for decades, nobody knew what it looked like alive because everything hauled up in a net arrived destroyed. In 2004, researchers at the Monterey Bay Aquarium Research Institute got a remotely operated vehicle in front of one and filmed it intact. The animal has a transparent dome on top of its head, a clear, fluid-filled shield, like a cockpit canopy, and inside it, 2 green tubular eyes. Tubular is the key word. A normal eyeball wastes most of its volume. A tube keeps the lens large while throwing away the parts of the sphere that don't contribute to looking in one direction. Large lens, long focal length, packed retina at the bottom, all of it pointed up, because up is where the last of the surface light is, and a silhouette against that faint blue is the only reliable way to find anything. The trade is field of view. You've built a telescope and you've given up looking anywhere but straight ahead. The barrelly's answer is that the eyes rotate inside the transparent dome, swinging from vertical to forward, which lets the animal track a target upward and then follow it into the mouth. Big aperture with a steerable mount and a clear pressure housing over the top of it. There's a relative of the barrel eye that went further, and for a long time it was known only from damaged specimens. Dolichopteryx longips, sometimes called the brown snout spookfish, lives in the deep open ocean. In 2008, a live one came up in a net off Samoa, in good enough condition to study, and a team led by Hans-Joachim Wagner published what was inside it in Current Biology the following year. Each of its eyes is split into 2 parts. The main tube points upward and works the ordinary way, with a lens. The second part, a lobe on the side, points down and outward, and it has no working lens at all. At the back of that lobe, there's a stack of small crystal plates arranged on a curved surface, a mirror, made of guanine in plates, angled so that light coming from below is thrown forward onto a patch of retina. It's the only vertebrate anyone has documented that forms an image with a reflector. Everything else with a backbone uses refraction. This animal runs both systems at once, in one eyeball, looking 2 directions with 2 different branches of optics, because the light coming down from the surface and the light flashing below it are different problems, and it decided to solve them separately. And the plates in that mirror aren't laid flat and identical. Their orientation varies across the curve, tilted from place to place so that each region throws light toward the same focus. That's the same thing a satellite dish installer does when he aims a panel, done at the scale of a crystal, across a curved surface without an aimer. So we have reflectors and we have lenses. The third thing you do with light, once you've collected it, is move it. And there's a family of devices for doing that, with a very specific name. An optical fiber is a strand with a core and a cladding, where the cladding has a lower refractive index than the core. Light entering the core at a shallow enough angle hits the boundary and gets reflected back in, over and over, and so it stays trapped and travels down the fiber even around bends. This is the physical basis of the entire internet. Every transoceanic cable is a bundle of these. Now go to about the same depth as the barrel eye, on hard bottom in the western Pacific, and find a sponge called Euplectella aspergillum. It has a common name that tells you something about how people react to it: the Venus flower basket. It's a hollow tube, maybe 8 or 10 inches long, made of a lattice of glass, and it's so regular and so fine that it looks manufactured. Dried specimens were given as wedding gifts in Japan, because a pair of small shrimp often live their whole adult lives sealed inside one. The lattice is silica. Glass, the same basic substance as a window, deposited by the animal out of dissolved silicon in seawater at whatever temperature the deep Pacific happens to be, which is a couple of degrees above freezing. In 2003, Joanna Eisenberg, then at Bell Laboratories in New Jersey, published a paper in Nature about the individual strands in that lattice. She'd been looking at them the way a materials person looks at things, and had noticed something. Each spicule has a core of pure silica about 2 microns across, wrapped around a thin organic filament at the very center. Around that core, there's a shell built out of many concentric layers, and the layers differ in composition, which means they differ in refractive index, core, cladding, index step, layers laid up around it. Those are optical fibers. Eisenberg's group put light into one end and got light out the other. They compared the performance against commercial telecommunications fiber and found the spicules stack up well, with a couple of advantages that come from how they're made. Manufactured fiber is drawn at high temperature and doped with materials that make it brittle. The sponge builds at ambient temperature, out of layers with organic material between them, and the result tolerates being bent and cracked far better than the industrial version. Snap a commercial fiber and it fails all at once. The layered spicule stops the crack at a layer boundary. I should be careful here because this is a case where the physics is solid and the biology is still open. We know the spicules guide light. What the sponge does with that has never been nailed down. There are proposals that the fibers carry light to symbiotic organisms, that they distribute the glow of bioluminescent bacteria to attract the shrimp that live inside, that light guiding is simply a side effect of a structure built for stiffness, and the animal gets nothing from it at all. Those are hypotheses. Nobody has run the experiment that settles it. The device exists and is measurable. The purpose is unresolved, and it's better to say so than to invent a story. The animals that unambiguously move light around are the ones that make it. About 80 to 90% of the animals in the open ocean can produce light. That's not a fringe capability down there. It's the norm. And once you can make light, you inherit every problem a lighting engineer has. Where to put the source, how to aim it, how to control the spread, how to change the color, and how to turn it off. Go to shallow water off Hawaii and find a bobtail squid, Euprymna scallops. It's about the size of a thumb. It buries in sand during the day, and at night it hunts in the shallows over pale bottom under moonlight, where anything swimming above the sand casts a shadow that a predator underneath can see from a long way off. Its answer is to glow on the underside, at an intensity that cancels the shadow. Counter-illumination? The light organ sits in the mantle cavity, and the light itself is made by a bacterium, Vibrio fischeri, which the squid farms in a set of internal crypts. Newly hatched squid come out sterile and have to acquire the bacteria from seawater within hours. And the organ is selective, admitting the right species and rejecting nearly everything else that tries to move in. Margaret McFall Guy and Edward Ruby built decades of work on that relationship at Hawaii and later Wisconsin, and it became one of the model systems for how animals and bacteria negotiate. But look at the hardware around the bacteria, because that's the part that matters here. Behind the bacterial crypts, there's a reflector built from stacked platelets of reflectin protein, throwing light forward instead of letting it leak backward into the body. In front of them, there's a lens, actual tissue lens, spreading the beam so it comes out diffuse rather than as a spot because a point source underneath you doesn't cancel a shadow, it advertises. Around the whole assembly, there's the ink sac positioned so it can be drawn across the organ as a shutter, cutting the output down or shutting it off. Reflector, diffuser, aperture control, and a light source U-culture and feed. That's a lighting fixture. If you took the drawing to a lighting engineer and covered the labels, they'd ask what the housing was made of and where the driver circuit sat. And the specification is severe because counter-illumination only works if the output matches the background on 3 axes at once. Intensity has to match, and the intensity of downwelling light changes with depth, with cloud cover, with the phase of the moon. Spectrum has to match, or you show up as a colored patch against blue. And the angular distribution has to match, because light from the surface arrives spread across a wide cone, and a source that beams straight down is visible from the side as a bright edge. Hit 2 out of 3, and you've made yourself more conspicuous than if you'd done nothing at all. That's the failure mode, and it's a nasty one, because the system fails toward being seen. Hatchetfish solved the same problem with more plumbing. These are small, deeply compressed fish, silver, shaped like the blade of a hatchet, and they hang in the twilight zone in enormous numbers. Along the bottom edge of the body, they carry rows of photophores, and Eric Denton, working out of Plymouth in England, spent years taking those photophores apart. Inside one, you find a light-producing chamber, a reflector wrapped behind it, a channel that carries the light away from the source, and at the exit, a filter that shifts the color of what comes out. Some of them include a structure that behaves like a half-silvered mirror, splitting the output so part of it goes one way and part another. The light is generated in one place and delivered somewhere else in a controlled beam, which is precisely what a light pipe is for. And in at least some counter-illuminating animals, there's a feedback path. The animal has photoreceptors that sample the downwelling light from above, and the output of the light organs tracks it. Turn the overhead light up in a tank and the animal brightens. Turn it down and it dims. That's a closed loop with a reference sensor, which is a substantially harder thing to build than a lamp. While we're on silver, look at the outside of that fish. A herring, a sardine, a hatchetfish, a jack, a tarpon. In open water, where there's nothing to hide behind, the best available camouflage is to be a mirror, because a vertical mirror reflects the light field back at whatever's looking, and the light field in the open ocean is roughly the same in every horizontal direction. You disappear by returning the room to itself. Denton and Michael Land worked out how fish do it, and the mechanism is a stack of guanine crystals in the skin with cytoplasm between them, the same class of structure as the scallop's mirror. A single stack with one spacing gives you a narrow band of color, which would make the fish look like a bar of shifting rainbow, which is the opposite of what you want. So the spacings vary, different stacks tuned to different bands, layered and mixed, and the sum across the whole surface comes out as broadband silver. There's a further problem underneath that one, and it went unnoticed for a long time. Light reflecting off a stack of layers tends to come back polarized, and a lot of the animals hunting in open water can see polarization. A fish that reflects a bright polarized patch into a predator's eye has undone its own camouflage, while still looking perfectly silver to us. In 2012, a group at Bristol led by Nicholas Roberts published work in Nature Photonics showing that herring and sardine use two different types of guanine crystal in their reflectors, with different optical orientations, combined in a way that cancels the polarizing effect. The reflection comes back broadband and neutral. That's a non-polarizing broadband mirror. And at the time the paper came out, it was better at holding that property across angles than the equivalent things we knew how to make. There's a mechanical detail I like even more. The crystal stacks stay vertical. The fish's body is curved. A mirror that follows the curve of the body would throw light upward from the back and downward from the belly, and the fish would flash like a piece of chrome. So in the regions where the body curves, the crystal platelets are held vertical anyway, tilted away from the skin surface, so that the mirror stays parallel to gravity even where the animal isn't. The camouflage is referenced to the world instead of to the body. Now the last thing to do with light, which is to control it in real time. The scallop's mirror is fixed. The fish's silvering is fixed. Cephalopods run reflectors they can adjust while you watch. In squid and cuttlefish skin there are cells called iridophores, and inside them are stacks of thin plates loaded with proteins called reflectins. Same principle again. A layered reflector whose color depends on the thickness and spacing of the layers. The difference is that the spacing is under nervous control. A team at Santa Barbara, working with Daniel Morse, traced the chain. A nerve releases acetylcholine. The receptor triggers a cascade that adds phosphate groups to the reflectin proteins. That changes their electrical charge, the proteins condense together, and as they condense, water is pushed out of the compartments holding them. Three things happen at once when the water leaves. The plates get thinner, the gaps between them get narrower, and the difference in refractive index between plate and gap gets larger. Thinner and closer means the reflected color shifts toward blue. Larger index contrast means the reflection gets brighter. So the same signal that tunes the color also turns up the intensity. And the whole range from red through to blue is available, and it's fully reversible, and the animal can cycle it over and over. An adjustable optical filter with an electrochemical drive, with brightness and wavelength on a single control input. The animal is running it in its skin, in seawater, at body temperature, with a switching mechanism that costs a phosphate group. I said earlier that the deep sea is monochromatic, blue and then nothing. There's an animal that turned that into a weapon. Malacosteus niger is a small black dragonfish, a few inches long, with a jaw arrangement that looks like a mistake and teeth that don't fully close inside its mouth. Under each eye it carries a light organ that produces red light. Far red, out past 650 nanometers, in a part of the spectrum that essentially nothing in the deep sea can see because everything down there has invested its entire visual system in blue. So Malacosteus is walking around the midnight zone with a searchlight on, and to every animal near it, the water is dark. The obvious question is how the dragonfish sees its own beam, since its ancestors had the same blue-tuned visual pigments as everyone else. The answer came out of work by Ronald Douglas, Julian Partridge, and colleagues in the late 1990s, published in Nature, and followed up in detail since, and it's the oddest solution in this entire section. Part of the answer is conventional. The fish has visual pigments shifted toward longer wavelengths, and a reflective layer behind the retina that gives incoming light a second pass at the receptors. The other part is that its retina contains a photosensitizer derived from chlorophyll. Chlorophyll, the molecule plants use to catch sunlight, sitting in the eye of a fish in permanent darkness, absorbing red light and transferring that energy to the visual pigment, which extends the range of what the eye can register, and the fish can't make it. The evidence points to a dietary origin. The compounds match derivatives of bacterial chlorophylls, and Malacosteus eats copepods, small crustaceans that graze on material containing them. So a molecule that begins in photosynthetic bacteria near the surface gets eaten by a copepod. The copepod gets eaten by the dragonfish, and the dragonfish installs it in its retina as an optical component. The specification reads like something out of a defense contract: emitter operating outside the receive band of every device in the theater. Receiver modified with an imported dye to recover that band. Result: an illuminated field of view that no other animal shares. That's optics. Reflectors tiled and tuned. Mineral lenses aligned to a crystal axis and corrected on a curve derived in the 17th century. Index gradients built out of protein concentration. Waveguides grown at 2 degrees above freezing. Lamps with reflectors, diffusers, and shutters, running on cultured bacteria and regulated against a reference sensor. Broadband, non-polarizing mirrors held vertical against the curve of a body. Tunable filters driven by a nerve. Everyone with a stated band, a stated tolerance, a way of failing. Now put the light away, because the next department is the one where things break. Muscle has a ceiling. It's a real number, and it doesn't move much across the animal kingdom. Muscle tissue, contracting as hard and fast as it can, delivers somewhere in the range of a few hundred watts of mechanical power for every kilogram of muscle. Yours does it. A tuna's does it. A shrimp's does it. The molecular machinery is broadly the same. The cycle time is broadly the same. And past that limit, muscle simply cannot go, which means that any animal that moves faster than that ceiling allows is not moving by muscle power at the moment of the movement. It's spending energy that was banked earlier. So you get a machine with 4 parts: a motor that works slowly, a spring that stores what the motor puts in, a latch that holds the spring loaded and keeps the motor from wasting the energy, and a release that lets go all at once. We know that machine. It's the crossbow, where a slow arm winds a windlass and a trigger releases it. It's the mousetrap. It's the shutter in a camera. Engineers have a phrase for the general idea: latch-mediated spring actuation, and it shows up everywhere in the ocean, done better than we do it. Start with the animal that does it hardest. Odontodactylus ciliaris is a mantis shrimp, which is a misleading name twice over. Stomatopods are a crustacean lineage that split away from the shrimp and the crabs a very long time ago and have been running their own experiment ever since. This species is about 4 to 6 inches long, colored like a spilled paint tray, green body, red arms, spotted tail, and it lives in a burrow in the reef with its eyes out front. The second pair of appendages, tucked under the head, ends in a heavy calcified club. And that club moves faster than almost anything else that has ever been alive. Sheila Paddock, then at Berkeley, later at Duke, worked out the mechanism with Wyatt Korf and Roy Caldwell and published it in Nature in 2004. To even film it, they needed high-speed cameras running fast enough that the strike, which takes a couple of thousandths of a second, spread out into a usable number of frames. Peak speeds around 23 meters per second. That's roughly 50 miles an hour, through water, over a distance of a few millimeters. The accelerations they reported run past 10,000 times the acceleration of gravity. The whole event is over in about 3 milliseconds, which is faster than your nerves can carry the news that it happened. Now no muscle does that. The power involved during the strike works out to hundreds of thousands of watts per kilogram of the muscle that drives it, which is something like 1,000 times what that muscle can actually produce. The gap is the spring. Here's the spring. On the upper surface of the appendage, there's a structure shaped like a saddle. Curved up along one axis, curved down along the other. The shape a mathematician calls a hyperbolic paraboloid, and the shape you see in a Pringle. That shape is used in architecture for roofs because it's stiff in a useful way, and it distributes load along both curves. The saddle is built in 2 layers. The outer layer is heavily mineralized, ceramic-like, and it's very good at resisting compression. The inner layer is mostly chitin fiber, and it's good at resisting being stretched. When the appendage is cocked, the saddle bends, the outer layer goes into compression, the inner layer goes into tension, and each material is loaded in the direction it's strongest. It stores elastic energy, the way a bow stores it, and it holds it. The motor is a large extensor muscle that contracts slowly, over tens of milliseconds, doing the loading. The latch is a pair of small hardened structures, sclerites, that hook and hold the appendage in the cocked position while the muscle keeps pulling. The muscle can pull as hard as it likes, nothing moves. Energy accumulates in the saddle and in the surrounding cuticle. Then, a small muscle releases the latch, and everything in the spring goes into the club through a 4-bar linkage, an arrangement of rigid segments and joints that converts a short movement at one end into a wide, fast rotation at the other. 4-bar linkages are in your car's suspension and in the hood of your car. The mantis shrimps is in its arm, and it's tuned for amplification. The result, measured directly by Patek and Caldwell with a force sensor the animals were happy to hit, is a peak impact force, over 1,000 newtons. Call it more than 200 pounds of force delivered by an animal that weighs about as much as a slice of bread. That's enough to break the shell of a snail, take the claw off a crab, and, in captivity, crack the wall of a glass aquarium, which is a thing that has happened often enough to be a known hazard among people who keep them. But the strike isn't finished, and this is where it gets strange. When the club moves through water that fast, the water can't close in behind it. The pressure in the gap drops below the vapor pressure of water, and the water boils at ambient temperature, forming a cavity of vapor. That cavity is unstable. It collapses violently, and the collapse delivers its own impact. So on the force trace, there are 2 peaks, the club and then the water. Patek and Caldwell measured the gap between them at roughly 400 microseconds, less than 0.5 of a second apart. The animal hits twice, and the second hit is free. It didn't come out of the spring. It came out of the pressure field the strike created, which means a mantis shrimp can damage prey it doesn't quite touch, and it means the club has to survive being hit by an imploding vapor cavity thousands of times over the animal's life. Remember the club. What it's made of is a materials problem, and the answer is worth its own section later on. Now, 23 meters per second is enormous for an animal. It isn't the record. The record belongs to a structure so small you'd need a good microscope to find one. And there are billions of them within reach of you right now if you're standing on any beach with a jellyfish washed up on it. Jellyfish, anemones, corals, and hydroids all belong to a group called cnidarians, and the group is named for the thing it's about to do to you. Every one of them carries stinging capsules called nematocysts, packed into cells along the tentacles. A nematocyst is a capsule with a coiled tube inside it. The capsule wall is a polymer of collagen-like protein, and it's held in a permanently stretched configuration, like a balloon inflated and then tied. Inside, there's a high concentration of small molecules that pulls water in osmotically, and the internal pressure has been estimated at around 150 times atmospheric pressure. The wall holds that, constantly, for as long as the capsule exists. That's the spring, and it's the whole capsule. When the trigger fires chemical and mechanical cues together, the lid opens and the wall contracts, and the tube inside turns inside out and shoots forward. Timo Nuchter and colleagues at Heidelberg filmed it in 2006 in the freshwater hydra, using cameras running at over 1 million frames per second. Published in Current Biology. Discharge complete in about 700 nanoseconds, less than 1/1,000,000th of a second. Acceleration during that period reaching more than 5 million times the acceleration of gravity. And at the tip, where the everting tube meets whatever it's aimed at, the calculated pressure exceeds 7 gigapascals. That's on the order of 1,000,000 pounds per square inch, in the range of what a bullet delivers at impact, which is how a structure a few microns across punches through the shell of a cope pod. It fires once. That's the detail that changes the shape of the whole thing. The capsule is single use. Once it's gone, the cell that held it is spent, and the animal builds a new one and moves it into position. In Hydra, cells that make nematocysts sit in the body column, mature there, then migrate out into the tentacles and take up station. There's a manufacturing line, an inventory, a delivery route, and a consumption rate. There's one more spring worth stopping on because it doesn't hit anything. Snapping shrimp, the alphids, are small, common, and if you've ever put your head underwater near a reef or an oyster bed, you have heard thousands of them at once. It sounds like frying fat, or like someone crumpling cellophane a long way off, continuous and everywhere. During the Second World War, the noise was loud enough to interfere with sonar and with the harbor detection systems the United States Navy was installing, and it prompted a serious research program at Scripps to work out what was making it. The answer eventually was shrimp. One claw on the animal is oversized, sometimes half its body weight, and it's built as a plunger and a socket. The shrimp cocks the claw open and holds it there against the pull of its own closer muscle, using a catch, and then lets go. For decades, the assumption was that the sound was the two halves of the claw hitting each other. It's such a reasonable assumption that nobody pressed on it. In 2000, Michel Versluis, Barbara Schmitz, Anna von der Heid, and Detlef Loos published a paper in Science that pressed on it. They ran a hydrophone and a high-speed camera together so they could line up the sound with the picture frame by frame. The sound doesn't happen when the claw closes. There's a gap, the claw shuts, and then a moment later, the noise. What the closing claw actually does is fire a jet of water out of the socket at something like 25 meters per second, about 55 miles an hour. That jet drops the local pressure below the vapor pressure of water. A cavity opens in its wake, and the cavity collapses. The collapse is the bang. The numbers on that collapse are worth handling carefully. You'll see figures over 200 decibels attached to snapping shrimp, and that's a real measurement. But underwater sound is quoted on a different reference than sound in air, so it can't be compared straight across to a jet engine or a gunshot the way you sometimes see it done. What's fair to say is that in terms of raw acoustic energy, snapping shrimp are among the loudest sources in the coastal ocean, loud enough that their collective racket is a genuine engineering problem for anyone trying to listen for something else. And then there's the light. In 2001, Loos, Schmitz, and Versluis reported in Nature that the collapsing bubble emits a brief flash, not visible to the naked eye, detectable with sensitive equipment. Light coming out of a bubble means the gas inside it was compressed hard enough and fast enough to reach extreme conditions, and their estimate put the temperature inside at collapse at least 5,000 Kelvin. They called it shrimpoluminescence, which tells you they were enjoying themselves. For scale, the surface of the sun sits around 5,800 Kelvin. This is a very small volume for a vanishingly short time, and it isn't heating the water around it in any meaningful way. The shrimp is not cooking anything. What it's doing is delivering a pressure wave that stuns a small fish or a worm at a distance of an inch or two. The prey is knocked down by a shock wave from a bubble, the shrimp made by moving a piece of shell. So that's the spring family. Slow motor, elastic store, latch, release, amplifier. Now the other half of mechanics, which is what you do when you want to move slowly, precisely, and with a lot of control. Every textbook diagram of a skeleton shows bone, rigid segments, joints between them, muscles crossing the joints. Muscle can only pull, never push, so you need something rigid to pull against and something to transmit the force. That's the vertebrate solution, and it's also, broadly, the robot solution. Links and actuators. The ocean is full of animals with no rigid parts at all that still generate precise, forceful movement. The trick is that water doesn't compress. Fill a closed space with fluid, wrap it in muscle, and now the fluid is the skeleton. Squeeze the sides, and the thing has to get longer, because the volume has nowhere else to go. Squeeze the ends, and it gets fatter. A sea anemone works this way. A worm works this way. The tube feet of a starfish work this way, and each one has a little muscular bulb behind it that acts as the cylinder. Then there's a refinement on that. And it's the one that produces the most impressive machines in the group. Take away the fluid cavity. Just use the muscle itself as the incompressible material, since muscle is mostly water and doesn't compress either. Now you have a structure where the same tissue is both the actuator and the skeleton. Bill Keir and Kathleen Smith at North Carolina gave it a name in the 1980s, a muscular hydrostat. Your tongue is one, an elephant's trunk is one, and an octopus arm is one, in the most complete form there is. The arrangement inside is 3 sets of muscle running 3 ways. Longitudinal fibers along the length, which shorten it, transverse fibers across it, which squeeze it narrow, and because volume is fixed, squeezing it narrow makes it longer. And oblique fibers wrapped in helices around the outside running both directions, which produce twist. That's it. 3 families of fiber. And from them you get elongation, shortening, bending in any direction, and torsion in either direction, in any part of the arm independently, with no joints anywhere. The extreme version is in squid. A squid has 8 arms and 2 tentacles, and the tentacles are different. They're kept coiled and hidden in pockets, and when a squid attacks, they fire out, grab, and haul back. Keir and Johan van Leeuwen filmed the strike in high speed. The stalk of the tentacle elongates by something like 50 to 80% of its resting length, and it does it in 20 to 40 milliseconds. Peak speeds over 2 meters per second, with accelerations around 250 meters per second squared, which is roughly 25 times gravity. The mechanism is the transverse muscle in the stalk contracting, which narrows the stalk, which forces it to lengthen because the volume can't change. The tissue that does it is specialized. Cross-striated fibers, built for speed instead of endurance, in a part of the animal where nothing else needs to be fast. A telescoping harpoon with a soft body and no rails. The octopus arm has the opposite problem, and it's a control problem rather than a power problem. An arm with no joints has, in principle, an infinite number of ways to get from here to there, and choosing among them is computationally brutal. This is a live headache in robotics, where soft manipulators are attractive precisely because they're compliant and safe, and difficult precisely because nobody knows how to plan their motion. The octopus sidesteps the general problem completely, and it does it by cheating, in the good sense of the word. Work by German Sumbre and colleagues in Israel, published in Science in 2001, showed that when an octopus reaches for something, it sends a bend traveling outward along the arm from base to tip. The arm behaves briefly, as if it had joints, because the bend defines a section that's straight, then a section that's curved, then another straight run. And when the animal brings food to its mouth, the arm forms what amounts to 3 temporary joints, a shoulder, an elbow, and a wrist, in whatever part of the arm the geometry calls for. It builds an articulated limb, uses it, and dissolves it. Some of the control lives out there too. An octopus has something on the order of 500 million neurons, and roughly 2/3 of them are in the arms, rather than the brain. Sever the nerve connection, and an isolated arm will still perform reaching movements when it's stimulated. What that describes is a distributed controller, with the loops closing out at the actuator instead of back at the central processor, which is an architecture our machines have been creeping toward for 30 years. Soft is one answer, armor is the other. An armor that has to bend is a properly hard piece of design. A seahorse doesn't swim well and doesn't need to. It hangs in seagrass and holds on with its tail. And the tail is one of the odder structures in the ocean because in cross-section it's square. Almost every animal tail on Earth is round. Round is what you get by default. Round distributes stress evenly, and it's the shape a tube wants to be. A square tail looks like a manufacturing error. In 2015, Michael Porter and Joanna McKittrick and Mark Myers at San Diego, with colleagues, published work in science testing whether the square was doing something. They took the real anatomy, which is a series of rings, each made of 4 L-shaped bony plates that overlap the plates of the next ring and slide against them. And they built the whole thing twice at larger scale on a printer, once with square rings, once with round ones. Then they bent both, twisted both, and crushed both. The square version won on every test that mattered to a seahorse. Grip was better because flat faces make contact with a stem along a line instead of at a point. Crushing performance was better. And the reason is a clean bit of mechanics. When you crush a ring of square plates, the plates can only slide along each other. 1 degree of freedom. Round plates can slide and rotate. 2 degrees of freedom, and the extra freedom lets the structure collapse sooner. The square rings absorb substantially more energy before anything permanently deforms. And the joints in the real tail sit exactly where the plates would otherwise fail. The seams are placed at the failure points, so the structure yields at hinges and springs back instead of cracking, which matters because the threat to a seahorse is crushing from a fish or a bird that takes the whole animal into its jaws and clamps down. The tail can be compressed to roughly half its width and recover. A chitin solves the same puzzle a different way. It's a mollusk that clamps to rock in the surf zone, and it's armored with 8 overlapping plates set in a tough muscular girdle. 8 plates instead of 1 shell means the whole armor can flex, which means the animal can seal itself against rock that isn't flat, which is the entire game when the surf is trying to take you off the substrate. Knock one off the rock and it rolls into a ball, plates outward like a pill bug. Now all rigid armor has one failure mode in common, and the arthropods live inside it: a crab, a lobster, a shrimp, a mantis shrimp. The skeleton is on the outside, and it's excellent. Stiff, light, cheap, waterproof, arranged as hard plates joined by flexible membrane at the joints. It's the same layout as a suit of plate armor, and it was in service 400 million years before anybody in Milan hammered out a knee cop. It cannot grow, so the animal has to shed it. Before a molt, a lobster reabsorbs some of the mineral from the old shell, secretes a new, soft one underneath, then splits the old one along a seam and drags itself out. Antenna, legs, gills, eye stalks, every one of them pulled backwards out of its own casing. Then it swells with water to stretch the new shell larger before it hardens. And for something like a week, it's soft and slow and edible, and it hides. A great many lobsters die during that week. It's one of the main causes of death in the group. That's the cost of a structure that gets assembled once and then can't be modified. To change it, you have to leave it. Keep that in the back of your mind, because the ocean has other answers to the same problem and they look nothing like this one. All right? Fluids. Every device so far has been operating inside water, and water is not a gentle medium. It's about 800 times denser than air and roughly 50 times more viscous. Push through it and it pushes back hard. It also carries away heat about 25 times faster than air does, which is why cold water is dangerous in a way cold air isn't at the same temperature. For a large animal, water is mostly an inertia problem. You accelerate a lot of mass and you leave a wake. For a small one, the world is completely different. Below a certain size and speed, viscosity dominates, and inertia becomes irrelevant. If a bacterium stops swimming, it stops dead, in a distance smaller than its own body. Coasting doesn't exist. Turbulence doesn't exist. To a copepod, water is thick and sticky, closer to honey than to what you experience in a swimming pool. Every piece of fluid machinery in the ocean is built for one regime or the other, and the ones built for the sticky regime are the least familiar. Start with the simplest animal that pumps, because it's simpler than you're ready for. A sponge has no muscles, no nerves, no heart, no gut, no organs of any kind in the sense you'd use the word. Aristotle wasn't sure it was an animal. For a long time, nobody was. And a sponge is a pump. The body is riddled with pores, and behind the pores is a network of canals leading to chambers, and the chambers are lined with cells called choanocytes. A choanocyte has a collar of fine projections around a single whip, a flagellum, and the whip beats. That's the entire motor. One flagellum in one cell, moving water a few microns at a time. There are millions of them in a sponge the size of your fist, arranged in thousands of chambers all beating. The chambers are wired in parallel off a branching canal network, and the network narrows and collects and finally exits through one or a few large openings called oscula, often raised up on a chimney. Every piece of that is a deliberate hydraulic layout. Wide inlet area across the whole body surface, so incoming velocity is low, and the animal can filter without wasting energy. Massive parallelism at the pump stage, because a single flagellum generates almost no pressure, and the only way to get flow is to run a huge number of them at once. Then a narrowing manifold that raises the exit velocity, and a raised chimney that dumps the used water up into the passing current, well clear of the intakes. That last one matters more than it sounds. A filter feeder that re-inhales its own exhaust is filtering water it has already stripped. The chimney is there to separate the outflow from the inflow. Sally Lays at Alberta and others have measured what these animals move, and the numbers are absurd for something with no muscles. Depending on species, a sponge can pump on the order of hundreds of times its own body volume every hour. Some estimates put a large individual at thousands of gallons a day. The pressures involved are tiny, a few pascals, which is less than the pressure change you'd feel walking up a single flight of stairs. What it lacks in pressure it makes up by running an enormous number of pumps in parallel, and by keeping the resistance of the plumbing low. And in the glass sponges of the deep, where there's a steady current, part of the work is done for free. Water moving past the raised chimney creates a pressure drop across the opening, which draws flow through the body without the animal spending anything at all. The shape of the body converts an ambient current into an internal flow. Anyone who has seen a prairie dog burrow with one raised entrance and one flush entrance knows the principle. The animal is using the same physics with a body instead of a hole. Bivalves take the same job and add a sorting stage. A mussel's gill is a sheet of tissue covered in cilia, and the cilia do two things at once. Some of them drive the current through the gill, which makes the gill the pump. Others catch particles out of that current and move them along a groove toward the mouth, which makes the gill the filter and the conveyor. And there's a sorting function on top. The animal separates what's worth eating from silt and rejects the rest as bound-up pellets. An adult mussel processes several gallons a day, and a dense bed of them can turn over the entire water column above it in a matter of hours. Filtering is low-pressure work. Getting out of the way of a shark is not. A squid moves by jet, and the jet is a proper piece of positive displacement machinery with a pump chamber, a set of valves, and a steerable nozzle. The chamber is the mantle, the muscular tube that makes up most of the body. It has two sets of fibers running through the wall. Circular fibers wrap around the tube, and when they contract, they squeeze the chamber and shrink its volume. Radial fibers run from the inside surface to the outside surface, and when they contract, they pull the wall thinner. And because the wall has to keep the same amount of tissue in it, thinning, it makes the tube wider. So the radial fibers refill the chamber and the circular fibers empty it, and neither one needs a bone to pull against. Now the valves. Water gets in through the gap around the neck, between the head and the mantle edge. During the power stroke, that gap has to be sealed, or the water squirts out the way it came in, and the animal goes nowhere. So there are flaps at the collar that close under pressure and open when the pressure reverses. One-way valves, working the way the valves in your veins work, opened and closed by the flow itself with no separate control signal. There's also a mechanical lock. On the inside of the mantle and the outside of the funnel, there are matched cartilage structures, a ridge on one and a groove on the other, and they engage to hold the funnel sealed against the mantle, so the only exit is through the nozzle. Divers who have handled squid have felt them disengage that lock. It's a stud and socket, and it clicks. Then the funnel itself, which is the part I'd want to look at if I were designing something. It's a muscular cone, and it can rotate forward, backward, off to the side, through a wide arc. The squid changes direction without changing its orientation, which means it can flee tail first at speed, while keeping its eyes and arms pointed at whatever it's fleeing from. And the opening can change diameter, so the animal can trade a wide, slow push for a narrow, fast one, which is a variable nozzle on a variable displacement pump. Every one of those is a component with a name in a catalog somewhere. The honest part of this is that jet propulsion is not efficient. There's a hard rule in fluid mechanics. To get thrust, you can either throw a small amount of water backward very fast or a large amount of water backward slowly. And the second option costs less energy for the same thrust. That's why a boat propeller is large and turns relatively slowly, and why efficient swimmers like tuna push a wide column of water with a big tail. A squid throws a small mass fast, which is the expensive option, and it pays. Squid have some of the highest metabolic rates of any marine invertebrate. They live short, burn hot, and grow at a rate that would look like a typo if you didn't know the animal. What they buy with it is acceleration. A jet delivers thrust instantly in any direction, from a standing start with no need to build up a swimming stroke, which is why the squid also carries a second propulsion system, the fins along the mantle, and uses those for cruising. 2 drive systems on one hull, one for range and one for the moment when range stops mattering. And some of them take it out of the water entirely. Several species in the family, that includes the neon flying squid, will jet hard enough to leave the surface, spread their fins and the membranes between their arms, and glide. Japanese researchers photographed the full sequence in the North Pacific: launch, glide, and re-entry, and the animals hold a posture in the air that looks deliberate. They can cover well over 100 feet. A squid using a water jet as a launch system and its own arms as a wing. Now the opposite end of the efficiency table, and it belongs to an animal most people file under primitive. The moon jelly, Aurelia aurita, is a bell of jelly with a thin ring of muscle around the rim, and the muscle is 1 cell layer thick. It contracts, the bell narrows, water is pushed out from underneath, and the animal moves. There's no muscle to open the bell back up. The jelly itself is the return spring. The mesoglea is elastic, it deforms during the contraction, and it springs back on its own, which means half the swimming cycle costs the animal nothing at all. That alone is a good design. Brad Gemmell, John Costello, Sean Collin, and colleagues found something better than that and published it in the Proceedings of the National Academy of Sciences in 2013. They seeded the water with particles and tracked the flow around swimming jellyfish frame by frame. When the bell relaxes and refills, it leaves a spinning ring of water underneath it, a stopping vortex. That vortex sits in the gap under the bell and pushes against it. And the animal, which at that point has finished its muscular effort and should be coasting to a halt, accelerates again. Free thrust, from the wake it made a moment earlier. The team measured it as roughly 30% extra distance per swimming cycle and estimated the effect on the cost of transport, the energy needed to move a kilogram of animal 1 meter, at an improvement of about 48%. With that included, the moon jelly has the lowest cost of transport ever measured in a swimming animal, lower than a fish, lower than anything with a spine. There's a second part of the mechanism that flips the usual picture. During the relaxation phase, the expanding bell draws water in from in front of the animal, and pulling water toward you creates a region of low pressure ahead. Low pressure ahead pulls. So part of the propulsion is the animal being sucked forward into a hole it opened rather than pushed from behind. An engine that recovers energy from its own exhaust, running on a spring made of the structure it's already carrying, in a body that's about 95% water. I have a hard time with people calling jellyfish simple. Simple is a statement about parts count. It isn't a statement about performance. Now, the fluid device that shows up more often in the ocean than any other, in more unrelated animals, for more different jobs. Once you learn to see it, you'll find it everywhere. Picture two pipes side by side, touching along their length, with something able to pass between them, heat or oxygen or salt. If the fluid in both pipes runs the same direction, the two get closer and closer to each other as they travel. And by halfway down, they've evened out and nothing more moves. Whatever you were trying to transfer, you got about half of it. And the second half of the pipe is dead weight. Run them in opposite directions, and the picture changes completely. At every point along the pair, the incoming fluid meets fluid that's slightly further along, so there's always a gradient. And transfer keeps happening down the entire length. You can move nearly everything from one pipe to the other. Counter-current exchange. It's in every heat recovery system, in every efficient building, in industrial chemical plants, in the design of every good radiator. And it's in fish. A fish gill is a stack of arches, each carrying rows of filaments, and each filament carrying hundreds of thin plates, called lamellae. Blood runs through the lamellae. Water runs over them, and the flow directions are opposite, which is why fish can pull off a number that ought to be embarrassing to us. A fish extracts up to around 80% of the dissolved oxygen from the water passing over its gills. Your lungs extract roughly a quarter of the oxygen in a breath. The reason a fish has to be that good is that water is a terrible place to find oxygen. A given volume of water holds something like 30 times less oxygen than the same volume of air, and it's 800 times heavier to move. So a fish is working far harder for a far poorer supply, and if it ran your respiratory system, it would suffocate. Your lungs are a dead end. Air goes in the same way it comes out. So fresh air always mixes with stale, and the gas in the deep part of the lung is never as good as the gas outside. It's a tidal system, and tidal systems can't do countercurrent because there's no steady flow to run against. The fish gill is a one-way channel, in at the mouth, out at the opercula, and one-way flow is what makes the whole trick available. Once you have a countercurrent exchanger, you can point it at other problems. Point it at heat and you get a warm fish, which shouldn't be possible. Here's why it shouldn't. A fish's gills are, by design, an outstanding heat exchanger with the ocean. Enormous surface area, tissue only a few cells thick, and the animal's entire blood volume passing through them on every circuit. Any warmth the muscles generate arrives at the gills and is handed straight to the water. That's the direct consequence of building the best gas exchanger you possibly can, and there's no way around it. A fish is obliged to run all of its blood through a radiator, continuously, forever. So bluefin tuna put a heat exchanger upstream of the radiator. Tuna keep their swimming muscle in an unusual place. In most fish, the red muscle that does the steady cruising work sits in a thin layer just under the skin, where it's inches from cold water. In tuna, it's buried deep, near the spine, insulated by the rest of the body. and the blood supply to that deep muscle runs through a structure called a rete mirabile, which is Latin for wonderful net, and the name is about 400 years old because anatomists have been finding these and being impressed by them for a very long time. A rete is a bundle of thousands of small parallel vessels, arteries, and veins alternating, packed close. Cool blood coming in from the gills runs one way. Warm blood coming out of the working muscle runs the other way, right alongside. Heat crosses over. The outgoing warmth gets handed to the incoming cold, and both of them turn around and go back where they came from. The heat never reaches the gills. It's caught at the border and sent back inside. A bluefin can hold its deep muscle well above the water it's swimming in extreme cases by something like 20 degrees Fahrenheit. Warm muscle contracts faster and produces more power, so the tuna can chase things in cold water that a cold-muscled fish couldn't catch. It's the reason bluefin can work the North Atlantic off Nova Scotia and then cross to the Mediterranean to spawn, operating across a temperature range that most fish would have to specialize into one end of. Then, in 2015, Nicholas Wegner and colleagues at the NOAA Fisheries Lab in La Jolla published something in Science about a fish nobody expected it from. The opa is a big, round, silver and red fish shaped like a hubcap, with bright orange fins, and it lives in the open ocean a few hundred to 1,000 feet down, in water around 45 degrees Fahrenheit. It looks slow. It looks like something built for hanging in cold water and waiting. Wegner's team found a rete inside the gill tissue itself. That's the move. Tuna warm regions of the body and let the rest run cold, and their hearts stay at water temperature like every other fish. The opa put the exchanger in the gills, at the exact place where heat is lost, wrapped around the vessels leading in and out. So the warming applies to everything downstream, which is all of it. Body core, brain, and the heart, which no other fish has been shown to keep warm. The opa runs about 9 degrees Fahrenheit above the water it swims in, all over, all the time. And the heat comes from the pectoral fins, which the animal beats more or less continuously using its swimming muscles as a furnace. The first fish anyone has documented with whole-body endothermy, and it took until 2015 because you have to catch one, get it aboard fast, and put probes in it before it equalizes. Now point the same architecture at gas instead of heat, and you get the strangest pump in the ocean. Most bony fish have a swim bladder. The reason is simple. Fish flesh and bone are slightly denser than seawater, so a fish left alone sinks, and holding position by swimming costs energy every second of every day. A gas-filled bag of about 5% of the body volume cancels that out, and the fish becomes neutrally buoyant. It floats at whatever depth it likes and spends nothing. The problem is what depth does to gas. Pressure in the ocean goes up by 1 atmosphere for every 33 feet. At 330 feet, a fish is at 11 atmospheres. At 3,300 feet, 101. Gas obeys that. Take a fish down and the bladder shrinks, buoyancy is lost, and the fish starts to sink, which makes it sink faster, which makes it worse. So the animal has to add gas. Adding gas to a container at 100 atmospheres requires a pump that can beat 100 atmospheres. The fish doesn't have one. There is no muscular structure anywhere in a fish capable of that pressure, and there's no reservoir of compressed gas to draw from. What the fish has is a wall of tissue called the gas gland, and a rete behind it, and what it does is chemistry. Start with the hemoglobin. In most vertebrates, acid makes hemoglobin let go of oxygen more readily, which is useful because working muscle produces acid and gets more oxygen delivered where it's needed. That's the Bohr effect, and you have it. Many fish have something stronger, called the root effect. Under acid conditions, their hemoglobin doesn't merely release oxygen more easily, its total carrying capacity collapses. It dumps oxygen into solution, and keeps dumping even when the surrounding oxygen pressure is already high, which is precisely the condition that would normally stop the process. So the gas gland pours acid into the blood passing through it, lactic acid and carbon dioxide, and the hemoglobin arriving there unloads its oxygen into the plasma. In a single pass, that alone can drive the dissolved oxygen pressure up toward 2 atmospheres out of essentially nothing. 2 atmospheres is not 100. That's where the REIT comes in. The blood leaving the gas gland, loaded with dissolved oxygen, runs back out through a bundle of capillaries lying directly alongside the capillaries, bringing fresh blood in. Opposite directions, as always. The oxygen in the outgoing blood diffuses across into the incoming blood and gets carried straight back into the gland, which means the oxygen keeps circulating in a loop instead of escaping, and every pass through the gland adds a little more, and the countercurrent geometry keeps it from escaping. The single pass effect gets multiplied over and over until the pressure in that small volume of tissue exceeds the pressure of the water outside the fish, and the gas has nowhere left to go except into the bladder. In a European eel, the REIT for this is built from tens of thousands of capillaries running side by side, each on the order of a centimeter long, packed into a structure you could hold between 2 fingers. That's the multiplier stage. That's why the length and the count matter. And because a fish also has to come up, there's a separate structure for venting. It's called the oval, a window in the bladder wall with its own blood supply and a muscular sphincter around it. Open the sphincter, expose the gas to blood that's low in dissolved gas, and it diffuses back out. The gland fills and the oval vents, and they're kept physically apart, so the 2 operations never fight each other. Fill circuit, vent circuit. Isolation between them. That's how you'd draw a pressurized system on a whiteboard. The same countercurrent idea shows up again for salt, and the animal it's most famous in is the shark. Sharks handle the ocean's saltiness by loading their blood with urea, which raises their internal concentration to roughly match seawater so water doesn't get pulled out of them. The side effect is that salt keeps leaking in. Something has to take it out against the gradient, and the kidney can't do it alone. So sharks have a rectal gland. It's a small finger of tissue off the back of the gut, made of tubules whose cells are crammed with the ion pumps that move sodium and potassium, and it secretes a fluid that's saltier than seawater. Pumping salt out of a body into an ocean that already has more salt in it is real work against a real gradient, and the gland exists to do exactly that and nothing else. That gland became one of the most studied pieces of tissue in physiology because it's the cleanest example anyone had of cells moving chloride across a membrane on purpose. A great deal of what we understand about that process in human tissue, including the channel that fails in cystic fibrosis, was worked out first in dogfish sharks at labs in Maine. So, fluids, parallel pump arrays with matched manifolds, positive displacement chambers with one-way valves, and steerable variable nozzles, elastic return springs recovering energy from a wake, countercurrent exchangers pointed at oxygen, at heat, at gas pressure, and at salt. Running at effectiveness numbers our equipment reaches only with careful engineering. Which raises a question I've been stepping around this whole time. What is all of it made of? Almost everything we build strong things out of, we build with fire. Steel comes out of a blast furnace at around 2,800 degrees Fahrenheit. Glass is melted near the same range. Structural ceramics get sintered in kilns hotter than that. Carbon fiber is made by cooking a polymer thread in stages until nothing's left but carbon, and the last stage can run past 3,000 degrees. Heat is how we get atoms to move into the arrangements we want. Nothing in the ocean has a furnace. Every hard structure down there is assembled at whatever temperature the water happens to be, which ranges from a bit below freezing to maybe 85 degrees Fahrenheit on a warm reef, at ambient pressure, out of ions that were already dissolved in seawater, by cells that lay the material down, molecule by molecule, from the inside. And some of what comes out of that process is better than what comes out of the furnace. Start with the one you've held. The inside of an oyster shell, or an abalone, or a pearl. Mother of pearl. The technical name is nacre, and it's a shame it's mostly known for looking pretty, because as a material, it's a genuine problem for materials science. Nacre is about 95% calcium carbonate by volume, in the crystal form called aragonite. Aragonite by itself is chalk adjacent. It's brittle. Drop a piece and it shatters. And if you tried to make anything structural out of it, you'd be laughed out of the room. The arrangement is what changes everything. The aragonite is laid down as flat polygonal tablets, roughly 5 microns across, and about 500 nanometers thick, stacked in layers like a brick wall. With a mortar of organic material between them that's only 5 to 20 nanometers thick. A vanishingly thin film of protein and polysaccharide holding ceramic bricks. Measure the energy it takes to drive a crack through that, and it comes out around 3,000 times the energy needed to crack the pure mineral. 3,000. Same chemistry, different arrangement. The reason is that a crack in nacre can't travel in a straight line. It reaches an organic layer and stops, because the soft layer absorbs and spreads the stress instead of transmitting it. To keep going, it has to go around a tablet, and going around means the tablets have to slide against each other, and they're covered in tiny bumps that resist sliding. And there are mineral bridges, connecting some of them through the organic layer. And the proteins in the mortar unfold in stages as they're stretched, each stage costing energy. So instead of one crack running through, you get thousands of tablets, each giving up a little ground, spreading the damage across a large volume. The shell deforms locally, whitens, and holds. This is the central problem in engineering ceramics, and it's been the central problem for a century. Ceramics are hard and stiff and hold up in heat and don't corrode, and they are frighteningly brittle. One flaw, and the whole part goes. Nacre is what a tough ceramic looks like, and it was arrived at by an animal that put it down in layers while sitting in the mud. Now go back to the mantis shrimp, because I left something unfinished. That club takes 1,000 newtons on impact, then takes a second hit from a collapsing vapor cavity a fraction of a millisecond later, and it does that thousands of times between molts. Any monolithic hard material would have cracked and failed early on. The question is what it's built out of. David Casalis and James Weaver and colleagues took clubs apart and published The Architecture in Science in 2012. And it's a layered composite with at least 3 distinct regions doing 3 different jobs. The impact surface is a layer of hydroxyapatite, crystalline calcium phosphate, the mineral in your teeth, and the crystals are oriented perpendicular to the surface, standing on end where the hit lands. That region is very hard, and the hardness falls off gradually as you move inward. A gradient, no interface, so there's no boundary where a crack could sit and concentrate. Underneath it is the part that makes the thing work. Layers of chitin fibers, each layer with all its fibers running one direction, and each layer rotated by a small angle relative to the layer beneath it. Stack enough of those, and the fiber direction sweeps through a full turn like a spiral staircase. Materials, people call it a Bouligand structure. A crack running down into that has to follow the weak direction, which is along the fibers, and the fibers keep turning, so the crack twists as it goes. A twisting crack travels much further to get the same distance down, and every bit of extra path costs energy, and the energy runs out before the crack does. Wrapped around the sides of the whole club, there's a third region of fibers running in bands around the circumference, holding everything in compression. Same idea as the iron hoops on a wooden barrel, or the pre-stressing in a concrete beam. Put the material under compression before it's loaded, and the tensile stresses that would open a crack have to overcome that first. There's newer work suggesting the layering does something else on top of all this, filtering the stress waves that travel through the club after an impact so that the damaging frequencies don't reach the tissue behind it. That's recent and still being tested, and I'd hold it loosely. The crack management is well established: hard surface with a graded transition, twisted crack core, circumferential pre-stress, and when the animal molts, the whole club is replaced. Then there's the material that holds the current record, and it belongs to an animal you've walked past 100 times. A limpet is the small conical shell stuck to rocks in the intertidal zone, the ones you can't pry off with your fingers. Limpets eat by scraping algae off rock, and they do it with a radula, a ribbon covered in rows of small teeth that they drag across stone, over and over, for years. Scraping rock destroys things. That's what rock does. Asa Barber, Dunlew, and Nicola Pugno, working at Portsmouth and Trento, cut tiny beams out of limpet teeth and pulled them apart inside an atomic force microscope, and published the result in the Journal of the Royal Society Interface in 2015. Tensile strength between 3 and 6.5 gigapascals. In numbers that mean something on this side of the Atlantic, roughly 400,000 to 950,000 pounds per square inch. That's the highest tensile strength recorded for any biological material. It beats spider silk, which had held the title, and it's in the range of the strongest fibers we manufacture. The structure is goethite, an iron oxide mineral, grown as nanoscale fibers embedded in a softer protein matrix. Thin fibers densely packed in a matrix that transfers load between them. The detail that impressed the researchers most was that the strength didn't change with sample size. Normally, bigger samples of a material are weaker, because a bigger sample is more likely to contain a flaw, and materials fail at flaws. That relationship is one of the most reliable things in engineering. Limpet tooth material didn't show it. The fibers are fine enough that a flaw large enough to matter apparently can't form. And here's the part that ties the section together. Those teeth wear out. Of course they do. They're scraping rock. So the radula is a conveyor. New teeth are formed continuously at the back end. They mature as they advance forward. They work, they wear. And the ribbon keeps feeding. A limpet is running a production line and a wear part replacement schedule inside its own mouth, permanently for its entire life. Chitons do the same thing with an even harder material. Their teeth are capped with magnetite, an iron oxide, and it's the hardest biological mineral anybody has measured, around 3 times harder than human tooth enamel. The cap is magnetite nanorods aligned along the tooth surface. Behind the cap, the hardness drops away in a controlled gradient, through a softer iron phosphate core, so the tooth is hard where it meets rock and tough where it meets the tissue holding it. And the chitin radula is a staged assembly line. Teeth are born at one end, and as they travel forward, they go through the mineralization steps in order, each region of the ribbon doing one stage of the job, until a finished tooth arrives at the working end. There's a paper from 2025 in Science identifying a specific protein that directs where the iron oxide gets deposited, which means we're now down to the level of the tooling that positions the mineral. An animal with no brain to speak of, running a multi-stage manufacturing process with the hardest mineral in biology, on a moving belt without stopping. There's one materials problem that's harder than all of the above. And if you've ever tried to fix something in the rain, you already know what it is. Glue doesn't work wet. The reason is more fundamental than it sounds. For an adhesive to grip, its molecules have to get right up against the molecules of the surface, close enough to bond. And any surface sitting in water has a film of water molecules stuck to it, clinging tightly, and that film has to be pushed off before the glue can touch anything. Water is also small and mobile, and there's an unlimited supply of it, so it keeps coming back. Industrial structural adhesives all say the same thing on the datasheet: clean, dry, abraded surface. Underwater repair in practice means clamps, bolts, and welds. Now go stand on any rocky shore in the northern hemisphere at low tide and look at the mussels. They're stuck to the rock, in surf that moves boulders, through winter storms, through freezing, through waves that arrive with enough force to knock a person down for years. Each mussel is held by a bundle of threads called the byssus, sometimes described as a beard, and each thread ends in a flattened plaque bonded to the rock. Herbert Waite at Santa Barbara has spent most of a career on how that bond gets made, and the chemistry at the center of it is an amino acid called DOPA. It's a modified version of tyrosine, and it carries 2 hydroxyl groups on a ring, which makes it unusually versatile. It can hydrogen bond to mineral surfaces. It can grab metal ions. It can be oxidized to cross-link with its neighbors and turn the whole deposit into a solid network. But the chemistry isn't the whole answer, and the process is where it gets clever. Watch a mussel lay a thread, and it presses the tip of its foot flat against the rock and holds it there. That press does something specific. It squeezes out the water underneath and creates a small sealed chamber against the surface. Inside that chamber, the animal isn't gluing underwater anymore. It made itself a dry room. Then it manages the conditions inside. The fluid it secretes is acidic, and it's chemically reducing, and both of those keep the DOPA from oxidizing too early. Let DOPA oxidize before it's on the surface, and it cross-links with itself, and you get a lump of cured resin that's bonded to nothing. So the mussel holds the chemistry in a reactive state until the material is where it's supposed to be, and then lets seawater in. And seawater is alkaline, and the change in acidity triggers the cure. That's a 2-part adhesive with a controlled pot life, applied inside a purpose-built dry chamber, cured on demand by exposure to the environment. The thread above the plaque is engineered too. The far end, near the rock, is stiff, around 10 times stiffer than the near end where it enters the animal. The soft end acts as a shock absorber, taking the sharp yank of a wave and stretching, while the stiff end holds the anchor. And the stiffness doesn't jump at a joint. It grades along the thread, because a sudden change in stiffness is exactly where things tear. Then there's the recovery. The thread contains iron ions, bound by DOPA, in complexes that hold parts of the protein network together. Under heavy load, those bonds break first, sacrificially, absorbing energy and protecting the backbone of the protein. When the load comes off, the bonds reform, and over the following hours the thread gets its stiffness back. The material repairs itself. Not as a figure of speech. You can load a byssal thread past its yield point, measure that it's gone soft, leave it in seawater, come back and measure it stiffer again. And when a thread does fail, the mussel makes another. It takes a few minutes. The animal carries hundreds of them, and it's constantly adding and releasing, walking slowly across the rock over weeks by anchoring ahead and cutting loose behind. The sandcastle worm builds with the same problem and a different solution, and its solution is closer to concrete. Phragmatopoma californica, it lives on the California coast in colonies that look like coarse honeycomb reefs, sometimes covering large stretches of rock. Each worm lives in a tube it built out of sand. Not sand it secreted, sand it collected. The animal reaches out, catches passing grains and shell fragments, tests them, positions them on the rim of its tube, and cements them in place, one grain at a time. The cement has to hold immediately, in moving water, on a wet mineral surface, with the next wave arriving in seconds. Russell Stewart at Utah worked out what's in it. The worm stores the components separately, in different cell types, at very high concentration. Some are proteins loaded with negative charge from phosphate groups. Others are loaded with positive charge. Kept apart, they're stable. Mixed at the moment of secretion, the opposite charges pull them together into a dense fluid that separates from the surrounding water instead of dissolving into it. That state has a name in chemistry, a complex coservate. It's a liquid that refuses to mix with water, which is exactly what an underwater adhesive has to be because anything that disperses is gone before it works. It's dense enough to sink onto the joint, thin enough to spread and wet the grain. Then, the setting. The secreted fluid is acidic. Seawater is alkaline. The pH shift changes the charge balance. The coservate stops behaving like a liquid, and within about 30 seconds, it is set into a solid. Full curing takes hours after that, as cross-links form and the material hardens further. 30 seconds to handling strength underwater on a wet surface with no clamping. And the cured joint is full of tiny pores, which sounds like a defect and isn't. The porosity gives the material somewhere to deform, and a joint that can deform a little absorbs energy instead of snapping. It's the same reasoning behind foam cores and structural panels. The last material I want to put on the table holds nothing together and glues nothing down. What it does is change its mind. Pick up a sea cucumber and it will go rigid in your hand like a length of hose that's suddenly full. Handle it more roughly and it does the opposite, going so soft in places that it seems to be melting. The dermis of a sea cucumber is called mutable collagenous tissue, and it's found across the echinoderms. Sea urchins use it to lock their spines upright. Starfish use it to hold a clam open for hours without spending muscular energy. Brittle stars use it at the base of an arm. The tissue is collagen fibrils in a matrix. What changes when the animal stiffens is how strongly those fibrils are bonded to one another, which is a completely different mechanism from muscle. Nerve endings in the tissue release proteins into the matrix that alter the bonding. One class of them, tensilin among others, drives it stiffer. Another class, including a protein named softenin, drives it softer. The changes happen in seconds and span a very wide range of stiffness, more than an order of magnitude in the measurements. So the animal has a structural material with a stiffness dial and a nervous system wired to the dial. The energy argument is the good part. A starfish pulling a clam open has to hold tension for hours. Muscle holding tension burns fuel the entire time. Locking the tissue costs a change of state and then costs nearly nothing to maintain. It's the difference between holding a door shut with your shoulder and putting a wedge under it. And at the far end of the range, the material can be softened past the point of holding together at all, which is the mechanism behind autotomy, a brittle star that drops an arm, a sea cucumber that expels its internal organs to distract a predator, a starfish shedding a limb. Those are controlled failures at a designated plane, triggered on command, in a material that was designed to be able to fail there. A failure mode you can fire on purpose. We do build something in that spirit, the explosive bolts that separate a rocket stage in flight, and those work exactly once and then they're spent hardware. Here it's a property of the material itself, dialed up and down all day. And when the animal drops an arm, it grows the plane back and can drop it again next year. That leaves one department, and it's the one where the ocean is furthest ahead. A sensor turns something physical into a signal. Judge one and you ask the same handful of questions every time. What's the smallest input it can detect, which is the threshold? What's the largest it can handle without saturating, which gives you the dynamic range? How much of its own noise does it generate, which sets the floor everything else has to rise above? How fast can it respond? And can it tell you which direction the signal came from? Those are the numbers on a data sheet. Let's use them. Run your hand along the side of a fish, and there's a faint line down the flank from the gills to the tail. Most people have seen it and never wondered about it. That's the lateral line, and it's a sensory organ we don't have anything like. Along that line and across the head in a network of channels sit structures called neuromasts. Each one has a cluster of hair cells, with fine projections sticking up into a blob of jelly called a cupula. Water moves the jelly bends the hairs, and the bending opens ion channels and produces a signal. The transducer is the same one that's in your inner ear, same cell type, same mechanism. The difference is that a fish has them on the outside of its body reading the water, and there are two kinds, wired for two different jobs. Some sit exposed on the skin, and those respond to how fast the water is moving past. The rest sit inside canals under the skin, and the canals connect to the outside through a line of pores. That neuromast never touches the outside water. It reads the difference in pressure between two pores, which means it responds to changes in flow rather than to steady flow. That second design solves a problem that would otherwise ruin the whole system. A swimming fish drags water past its own flank constantly. If every sensor read raw velocity, the fish's own movement would swamp everything. Burying the sensor in a canal with two openings builds a filter into the anatomy. Steady flow presses equally at both pores and cancels, while a sudden change presses unevenly and gets through. The fish is filtering out its own motion using the shape of a tube. The sensitivity is in the nanometers. Displacements of the cupula far smaller than the wavelength of visible light produce a response, which is enough for a blind fish to build a picture of a room. The Mexican tetra has cave populations that have lost their eyes entirely, over many generations in total darkness. Drop one into a tank it has never seen, and it will make a series of quick glides, then settle down and navigate the space cleanly, avoiding walls it has never touched. What it's doing is pushing a pressure field ahead of itself and reading how that field comes back off the surfaces around it. The fish makes the signal and reads the echo, and the medium is pressure rather than sound. The lateral line is also how a school stays a school. Take it out of the picture and the spacing degrades. 100,000 fish turning as one unit are in large part feeling each other. Now the sense that isn't on our list at all. Sharks, skates, and rays have pores scattered over the snout, hundreds of them. Dark spots you can see clearly on a shark's nose. Each pore opens into a canal filled with a clear jelly, and each canal ends in a small chamber packed with sensory cells. They're called the ampullae of Lorenzini, after Stefano Lorenzini, who described them in 1678 and had no idea what they did. Nobody did, for almost 300 years. Guesses included pressure detection, temperature, and glands of some kind. Adrianus Calmine worked it out in the 1960s and 70s. They detect electric fields. Every living animal leaks electricity. Muscle contraction produces small voltages. The ion gradients across a gill membrane produce a standing field. A fish sitting perfectly still buried in sand, holding its breath as much as it can, is still a weak electrical source because being alive requires moving ions across membranes. Calmine ran the experiment that settles it. He offered sharks a flounder buried in sand, a flounder sealed under an agar barrier so no scent could escape, and a pair of electrodes with nothing behind them producing a comparable field. The sharks attacked all three, including the electrodes with nothing to eat. The sensitivity in his work came down to fields on the order of 5 nanovolts per centimeter. That number is hard to hold. The illustration people usually reach for is a flashlight battery with one terminal in one part of the ocean and the other terminal 1,000 miles away, and the shark detecting the field that spreads between them. Take that as an illustration rather than a measurement. The measurement itself is the one that matters, and it's small enough that the shark is operating close to the electrical noise floor of the ocean. The physical layout is doing real work. The canals are long, and they run from a pore on the surface to a bulb deep in the head, which means the animal measures voltage across a long baseline, and a longer baseline across the same field gives a bigger reading. The canals point in many different directions, which turns the collection into a directional array, and the jelly inside them has to carry the signal along that length without losing it. In 2016, a group including Marco Rolandi at Washington and colleagues published a paper in Science Advances about that jelly, and it turned out to be worth a paper of its own. The jelly is one of the best proton conductors ever measured in a biological material, within a small factor of Nafion, the synthetic polymer used in fuel cells, which people have spent decades optimizing. The wiring in the shark's nose is a specialized conductive material, and nobody had bothered to test it until 40 years after we knew what the organ was for. Sharks also do something with smell that most people get wrong. The usual claim is that a shark can smell a drop of blood in a swimming pool, and the numbers are real enough at the level of parts per billion for some compounds. But concentration alone is close to useless for finding anything, because ocean odor arrives as a chaotic mess of filaments, torn up and stirred around by turbulence. And the strongest patch is often nowhere near the source. Jane Gardner and Jella Adama, working at Boston University and the Mote Lab in Florida, tested what sharks actually steer by. They fitted dogfish with tubes delivering odor to each nostril and controlled the timing between them. The shark turns toward whichever nostril got the smell first, with delays as short as a fraction of a second. It's reading arrival time, the same information your brain uses to tell which side a sound came from, applied to chemistry. Lobsters take sampling further. A lobster's antennules are covered in fine chemosensory hairs, and at that scale, water is thick and sticky and refuses to flow between closely spaced hairs. So the lobster flicks the antennule fast on the downstroke. The speed of the flick changes the flow regime enough that water penetrates between the hairs. Then, the slow return stroke leaves that parcel of water trapped in there, held against the sensors. A sniff, built entirely out of changing the fluid conditions by moving quickly and then slowly. Mimi Coyle at Berkeley worked this out with flow modeling and physical models, and it's a beautiful bit of biological plumbing, because the animal is picking a stroke speed that puts the physics on its side instead of trying to overpower it. Then there are the sensors for movement itself. Almost every animal that needs to know which way is up carries the same device, a chamber lined with hair cells, and inside it, a dense mineral mass resting on them. The mass is heavier than the fluid around it. Tilt the animal, and the mass shifts and presses on different cells. Accelerate and inertia holds it back, while the chamber moves around it. That's an accelerometer and an orientation sensor in one. Jellyfish have them around the bell rim. Cephalopods have them in the head, with an extra system for detecting rotation. Fish have them as otoliths, the ear stones, and the fish version does something extra. Otoliths grow by adding layers, and the layers go down on a daily cycle, in rings, like a tree, which means every fish is carrying a physical record of its own life in its skull. Count the rings for age. Read the trace chemistry layer by layer, and you can reconstruct the temperature and water chemistry it lived through and roughly where it was. A sensor that's also a data logger, running continuously, with a resolution of 1 day. I want to end this section on the one that ties back to where we started. Mantis shrimp again. Their eyes are the most complicated optical systems known in any animal. Each eye is divided into 3 parts, so a single eye sees a point in space with 3 regions at once and can judge depth on its own. The middle band carries rows of specialized receptors, and the animal has far more color channels than we do, which turns out to work differently from how everyone assumed. But that's a different story. The part that belongs here is polarization. Light waves vibrate in a direction. Sunlight underwater is partly polarized, reflections are polarized, and some animals are polarized. Plenty of ocean animals can read linear polarization, the kind where the vibration stays in one plane. Mantis shrimp read circular polarization, where the direction of vibration rotates as the wave travels. They're the only animals known to do it. To detect circular polarization, you first have to convert it to linear polarization, and the device that does that is a quarter-wave retarder. We make them out of specific crystals cut to specific thicknesses. The catch is that the thickness only works for one wavelength, so a manufactured retarder is tuned to a color, and away from that color, it degrades. Nicholas Roberts, Tsir-Hui Chiu, Justin Marshall, and Thomas Cronin measured the structure in the mantis shrimp's eye that does the job, one of the photoreceptor cells sitting above the others, in a particular row of the middle band. It behaves as a quarter-wave retarder, and it holds its performance across the whole visible range. Achromatic, where ours are tuned. They published it in Nature Photonics, and the framing in the paper was straightforward. The animal's version outperforms the manufactured version on that specific property. There's one more sensor, and I saved it because it's the one where the engineering is in the part nobody would have looked at. Harbor seals hunt in water that's often dark and often cloudy. Fish are quiet and quick and don't come to you. So how does a seal find one at night, in murk, from a distance? Guido Denhardt and colleagues in Germany answered that in a paper in Science in 2001, and the setup was elegant. They trained harbor seals, blindfolded them with a mask, put headphones on them to remove sound, and then sent a small remote-controlled submarine across the pool. Then they released the seal. The seals found the submarine's trail and followed it. Not occasionally, around 80% of the time, tracking the path the vehicle took, including its turns, with no vision and no hearing. What they were following is the wake. Anything moving through water leaves a structured disturbance behind it, a train of small vortices that hangs in the water for a surprisingly long time, tens of seconds, and holds the shape of what made it. A fish leaves a trail. The seal reads it the way a dog reads a scent line on the ground. The sensor is the whiskers, and the whiskers are where it gets specific. Most mammal whiskers are smooth cones. Harbor seal whiskers are not. In cross-section, they're elliptical, and along their length they undulate, wider, then narrower, then wider, with the wide and narrow axes offset from each other so the whole thing has a wavy, twisted profile. If you saw one enlarged, you'd assume it was deformed. Wolf Hankey and colleagues put those geometries in flow tanks and measured what they do. A smooth cylinder in moving water sheds vortices off alternate sides, and that shedding makes the cylinder vibrate. Every flagpole does it. Every antenna on a car does it. A whisker doing it would be shaking constantly from its own passage through the water, and that self-generated shaking would bury any signal coming from outside. The undulated geometry breaks up the shedding. The vibration drops by a large factor compared to a smooth whisker of the same size. That's noise floor engineering. The animal isn't making the sensor more sensitive, it's making the sensor quieter, so that the same sensitivity is usable. Anyone who has worked on instruments knows which of those two problems is harder. And now I want to put all of it on one table because there's something in the pattern that took me a long time to see. Go back through them. The mirror in the scallop's eye, tiled and tuned. The calcite array in a brittle star's armor with every lens aligned to the crystal axis. The gradient lens made of protein concentration. The waveguides grown at 2 degrees above freezing. The saddle spring and the 4-bar linkage. The capsule held at 150 atmospheres for the whole life of the cell that carries it. The countercurrent multiplier that pushes gas into a bladder against 100 atmospheres using nothing but acid and geometry. Nacre. The Bouligand core of the club. The goethite fibers in a limpet's tooth. The 2-part adhesive applied inside a chamber the animal makes by pressing water out of the way. Collagen, with a stiffness dial. Whiskers shaped to stop themselves ringing. Every one of those has a specification. Everyone has a working principle you can name. Everyone has tolerances, and everyone has a way of failing. So when I compare that list to the equivalent list from our side, the difference I expected to find was sophistication, some measure of how clever the design is. That's the comparison everybody reaches for, and it's the wrong axis, because on that axis, the two lists are roughly even. We have things they don't. They have things we don't. Some of theirs beat ours on a specific number, and some of ours beat theirs by an enormous margin. The real difference is in how the object comes to exist and what happens to it afterward. Ours are assembled. Parts get made somewhere in a controlled environment by a separate machine. The parts get brought together and joined. At some moment, the assembly is complete, and from that moment, the object is finished and begins slowly to degrade. Everything after that is maintenance, and maintenance requires stopping. You take the aircraft out of service. You pull the pump off the line. You send the lens back to the shop. Theirs are grown, and the growing never stops. The scallop's mirror goes in tile by tile while the eye is in use, and when a crab takes the eye off the mantle edge, the animal builds another one, mirror and all, and the rest of the array covers the gap in the meantime. The limpet's teeth are on a belt, being born at one end and worn away at the other, continuously, for the animal's entire life. The chitin's radula runs a staged assembly line where the tooth advances through the mineralization steps one position at a time. Hydra manufactures stinging capsules in the body column and walks them out to the tentacles to replace the ones that fired. The muscle's iron bonds break under a wave and reassemble between waves, so the thread recovers overnight from damage it took that afternoon. The sea cucumber changes what its own skin is made of in the time it takes you to blink. There's no moment in any of those where the object is finished. And there's no separate factory. The thing that makes the device is the device. The tissue that grows the mirror is part of the same animal that's looking through it. No supply chain, no parts inventory, no shipping, no assembly step, no commissioning. The specification is met by a process that keeps running instead of by an operation that was performed once. The lobster is the exception that shows the cost of doing it our way. Its armor really is assembled once. It's rigid, it's excellent, and it cannot be modified. So every time the animal needs a bigger one, it has to climb out of the old one and stand there soft and defenseless while the new one hardens, and a lot of them die doing it. That's what a once-assembled structure costs a living thing. Everything else down there is dodging that bill by never finishing, which is why repair barely means the same thing on the two sides. On our side, repair is an interruption. Down there, repair is indistinguishable from operation, because the process that lays down the material never stopped in the first place. The scallop can't take the eye offline to fix the mirror, so it evolved a way to fix the mirror while looking through it. The limpet can't stop eating to change teeth, so the teeth change themselves while it eats. I think that's the real gap. And I've come to believe it's a deeper one than sophistication, because sophistication is something you can catch up on with enough people and enough time. And this is a difference in what kind of thing an object is allowed to be. The word technology comes from the Greek techne, which meant craft or skill, or the knowledge of how to make something. For most of the time we've had the word, we've quietly assumed the knowledge had to sit in somebody's head. There's no head in a scallop worth the name. There's no head at all in a sponge. The knowledge sits in the structure and in the process that keeps building it. And it has been sitting there working in salt water for a very long time before anyone was around to be impressed. I've done all the talking here, and I'd like the argument to run the other way for a while. Here's the specific thing I'd like in the comments. Out of everything on that list, pick the one you would put into production tomorrow if the manufacturing problem were solved, and say what you'd point it at. The adhesive that sets in 30 seconds on a wet surface. The material that changes stiffness on a signal. The pressure multiplier that fills a container against 100 atmospheres without a pump. The mirror that gets built while it's being used. I have my own answer, and it's the boring one, the muscle glue. Because I've spent enough time trying to fix things in the rain to know what that would be worth. And tell me the one I left out. I know I left some out. There are whole families of these I couldn't fit. And the ones I keep hearing about from people who work on the water are usually better than the ones in the papers. And if you want more of these built at this length, the like and the subscribe are the two signals that tell me to keep them whole instead of chopping them into pieces. Long is a choice. It's the one I'd rather keep making. Now let me take you back to the beginning, because there's something I didn't tell you. The scallop in the eelgrass. Shell open 1/4 inch, 200 small blue points along the mantle edge, catching the light. The first time, that's a curiosity. A strange animal with too many eyes. Doing something we don't have a word for. Here's what's actually in front of you. 200 reflecting telescopes, each one under 1/10 of an inch across, each with a mirror of square crystals laid edge to edge in 30 layers, tuned to the color of the water in that particular bay, shaped off-sphere to hold the focus, feeding 2 retinas at 2 different distances. Some of those eyes are older than others. Some are being repaired right now. 1 or 2 at the back of the row are being built from nothing, on a rim of tissue out of dissolved material, in the dark inside the shell, while the animal keeps watching the water with the rest of them. Nobody switched anything off to do it. Nobody will. And then a shadow crosses, and the whole array reports at once, and the shell claps shut and opens and claps again, and the animal lifts off the sand and goes bouncing away through the eelgrass, ridiculous and perfect, carrying 200 working instruments it never has to stop using in order to keep.